Unit 5.1 is all about mean value theorem. So in this video, we're going to go about that and find the difference or go over the difference between mean value theorem and intermediate value theorem. So the mean value theorem basically just says that in a function that is continuous and differentiable, there's some value of c where the derivative of that just equals the average rate of change. So in this case, we got a and b, and then this orange line is just our regular function, which is continuous and can be derived. And then let's just say these two red points right here is just like a value of c. And then if we take the derivative of that, this just means that our derivative is the same as the average rate of change of the whole function. So that's really what mean value theorem is all about. And then intermediate value theorem, it's a little bit different. It's literally just saying that it guarantees a value of c and f of c between an interval of a of b if the function is continuous. So right here, this is just an example of a continuous function where we have a and b and then just some value of c that's guaranteed. So we're going to go over some couple of questions about intermediate value theorem and mean value theorem, and this is going to be a short video overall. First question: skater Sully is riding a skateboard back and forth on a street that runs north and south. The twice differentiable, I'm going to highlight this, function s models Sully's position on the street measured by how many meters north he is from his starting point at time t, measured in seconds for the start of his ride. Table below gives values of s of t at selected times t. So part A asks, from an interval of 0 to 20, must there be a time t when Sully is 2 meters south of his starting point? Justify your answer. So this one, part A, is all about intermediate value theorem, because our function is basically just a position function, and we'll go over part B, how that has to do with mean value theorem. So part A is just asking if there's a guaranteed value where Sully's position will be 2 meters south. So I'm going to go to the question, what I highlighted. It says twice differentiable, meaning that the function is continuous. If the function can be derived, then it's continuous. So I'm going to write that right here. So s of t is continuous. And it's asking, must there be a time t when Sully is 2 meters south of the starting point between the interval from 0 to 20. So we're just looking at this time range. So s of 0 equals 0, and s of 20 equals -5. And it says, is there a time t where Sully is 2 meters south? We can say yes, because there is a value of c. So I'm just going to write this down here. So there is a value of t, or a time t, such that s of t equals -2, where t is going to be in between the interval of 0 to 20. Where t will be in the interval of 0 to 20. And this is going to be intermediate value theorem. B is going to be a little bit different. Okay? And then I'm going to remove that. Part B is asking, from the interval of 30 to 60 for time t, is there a value where Sully's velocity is 1.1 meters per second? Justify your answer. So we're going to focus on this time interval, and it's asking us when Sully's velocity is 1.1 meters, which means our derivative, because our original function is just position. So what I'm going to do is I'm going to find the average rate of change, and then I'm going to find the calculation for that. So we're going to do s of 60, so 40, and then s of 7, so s of 60 minus s of 30 is just a 7 over 30, which is just 33 over 3, or 33 over 30, which is actually just 1.1. So there is indeed a time t where Sully's velocity is 1.1. Our average rate of change equals our derivative. So therefore, we can say yes. And then you can say, according to MVT, there is a time t such that s prime of t equals 1.1. And then you can say that the function is differentiable and s of 60 minus s of 40 divided by 30 equals 1.1. So those are the differences between these two parts. And then we're going to go on to our next questions. So in these ones, we're just going to literally just use MVT and find where the derivative is equal to the average rate of change. So for this, you're just going to plug in your value. So let's just say y is f of x. And then on the interval of -4 to -2, so you just do f of -2 minus f of -4 all over -2 plus 4. And then you just set that equal to the derivative. So 2x minus 5. So I'm just going to quickly plug that in, and then I'll show you what to do after that. After plugging in the values, you will get -11, and then you just set that to the derivative. And then the question is just asking us what value of x is where the derivative equals average rate of change. So we just solve for x, and then you will just get x equals -3 as your answer. And if you want, you can plug that back in into the derivative. So this will just get you simply -11. And that's it for number 4. And then we'll go on to number 5. And then I'm going to do the same thing, just do y as f of x. And then it's making us find the mean value theorem derivative and average rate of change on the interval of 0 to pi. So we're just going to do f of pi minus f of 0 over pi. And then I'm going to equal that to the derivative, which is just 3 cosine 3x. And then I'm just going to quickly plug that in. So let me do that. After doing so, you're just going to get 0 as the average rate of change. And then again, just solve for the value x. So you're going to get cosine 3x equals 0. Take the inverse, and then that'll just be cosine inverse equals 3x. And then you know that cosine 0 is going to be 3 or a couple possible values. So in this case, I'll just give you the answer straight away. So it'll be 3x equals pi over 2, and then 3 pi over 2, and then 5 pi over 2. And then once you divide everything, it would just be pi over 6, pi over 2, and 5 pi over 6 as your x values. And that's it for these two questions. And then we're going to go on to one last question, and then I'm going to read it out and explain what to do. So let g be a continuous function. The graph of the piecewise linear function g prime, the derivative of g, is shown above for the interval -4 to 4. Find the average rate of change of g prime of x on the interval -4 to 4. Does the MVT applied on the interval guarantee a value of c from -4 to 4, but not including them, such that the second derivative of g prime, or g of c, is equal to this average rate of change? So we have an issue here. When we look at this graph, I can see we have 1 and 2 corners. Okay, so this question is asking, can the average rate of change of this function equal the derivative of the other function? So this is simply just g prime of x. It's asking if the average rate of change of this function will equal the derivative of that value. So in this case, if you remember from previous unit 2 I think, you know that you can't take the derivative of a graph when there's like a corner. So you'd have to say no for this. No, and then because cannot take derivative of function due to corners, and that's it. So 5.1 is just mean value theorem, and then if you forgot what it was, again, it's just where the derivative of the function of some value equals the average rate of change, and that's really it. So I'll be posting 5.2 maybe like Tuesday, Wednesday, but we'll see. Alright, see you guys later.